So I hope you're all set up and going, have downloaded NODEMaple and installed the library. So let's get started with the timber constructions. So we're going to have a look at the ultimate limit states now. So to start that, you're going to open, you need to open NODETimber. And you have to go to workbook, and on the left hand side you see those three calculation sheets which have been designed. The first one we have had a very quick introduction in the last video. Is going to just have material properties and section properties. We are going to have a very quick walk through the chapter 6 of the ultimate limit states design according to the Eurocode. So if you're going to switch quickly to the Eurocode, we're going to deal with section 6, ultimate limit states, and all of those points here, items here, are dealt with in the Maple sheet. So we're going to have a quick look at tension parallel to the grain, perpendicular to the grain, compression parallel and perpendicular to the grain, bending, shear, torsion. Then we have the combination states with compressed stresses at an angle to the grain and bending and axial tension and compression. Stability of the members, those are also included and implemented in the design. And we have some special members with varying cross sections or curved shapes, and the notched members with notch at the support. So let's just go back to the sheet. Just a very quick introduction about how these sheets are put together. You have chapters. The chapters, the first one is the general information, which deals about a short introduction, what are you going to expect here. Then we have the input data. The general information in the input data is just a cutout from the Eurocode about some explanations. Everything here is taken from the Norwegian translation, so bear that in mind. We have the import and export, which I've talked quickly about in the last section. Very short summary. If you want to save calculations, you always should not only save them as the calculation sheet itself, the Maple, but also make the export to a file which can be imported in a new version at a later point. So you have the project data, material data, section data, and calculation data, which can be saved. You also have the possibility to export some of the calculations, depending on which kind of calculation we're talking about. The project information, project number, title, client, and so on. And here we have a very important stuff. I have talked about code and data previously. As I said, these calculation examples are a mixture of code and data mixed and code and data splitted. This table, a data table, stores in fact all the calculations which you have done in the sheet previously. So if you close this Maple sheet and you open it again, the state of the calculation from the previous calculation is saved here in this data table. Sometimes it can happen that the data in the sheet gets corrupted. In that case, you need to reset these settings. Because if the calculations is started with a corrupt data set, you're going to run into some troubles, you're going to get error messages. So sometimes the only way to go further on and make these calculations work again is to reset the settings. In that case, you're deleting all the stored data in the worksheet, and you can start from scratch more or less. We have the material and section data for the input. In general, you just can calculate one section at a time. So regardless if you're dealing with different load cases, which could be bending, shear, and moment combined, or each for itself, or even perpendicular and in grain direction, you just can calculate one section at a time. And one section at a time does also mean this section needs to have the same strength class, service class, and load duration classes. Okay, the next part is the buckling and lateral torsion buckling lengths. So we are dealing about one of the points which is dealt in that part, the 6.3. So we have buckling length around the y-axis and around the z-axis, and you also have the lateral torsional buckling for bending around the y and z-axis, which are defined here. Sometimes, if you don't have any buckling problem or a lateral torsional buckling problem, you should set this value very low. But you can't actually set it to 0 because some of the formulas don't like the value 0 actually, so you're getting an error message. But 0.6 should usually be quite okay. We have the continuous and discrete supports. These are just getting valid if you have compression perpendicular to the grain. So this is also chapter 6.1.5. Then you have to check the 6.2.2, compression at an angle to the grain. Again, this is just going to have an effect if there is an actual angle in your profile. Chapter 6.4, members with varying cross-section or curved shapes. Here again we have these three types of beam geometry, and the values which are necessary for the input are also described down here. So you have the curved, you have the single tapered beam, which is that one. You have the double tapered beam, which is that one. You have the curved beam, this one, and you have the pitched cambered beam, which is that one. So these are, if you don't have any of them, you just need to pick the first choice here. So next stuff is 6.652, which is the end notched beam, where you have two different possibilities here. And more or less this was the system input. So you have the project data, you have the system data. Next chapter are the loads. Regarding loads, you can have different type of loads, and you can either give them names or numbers. You need to have at least one load case. So if you're trying to delete the last one, it gives an error message. So we have the load case, we have the angle of the load regarding to the grain direction. So 0 degrees is in grain direction and 90 degrees would be perpendicular to the grain direction. You have hard-coded load safety factors for the permanent load and for the variable loads. And you can either input the dimensioning load already, or you can give an input of the permanent loads and the variable loads. So if I put in a value here and a value there, then this value is going to be calculated automatically. If you give an input to the dimensioning value, dimensional force, directly, then those two values here are going to be grayed out. So you need to actually delete this value for opening up input fields here. After the loads, we are going to have a look at the material and section properties. These are calculate values already in the first sheet, which I've showed you in the previous video. These are calculated values. And then we already go to the calculation. The calculation you can do automatically, or you can calculate manually. As there are more load cases, usually when you do a a calculation, just the calculation, the active calculation is going to be calculated. But there is also the possibility to calculate all load cases in case you have more than one. And in that case, you are getting this value in addition. So let's say the active value is calculated here, of the active load case. But if you have added something in additional, more than one load case, and you press the calculate all load cases, then this value switches the color from gray to either green or red or yellow, depending on the kind of factor for the load. So for values below 0.8, which means 80% of the capacity, all values are getting green. Between 80 or 90% to 100% is going to get orange, and over 100% it's getting a red color. So you immediately get a feedback about the utilization of the load case. In addition to the short summary, you're also getting result details. Yeah, one thing which is also important is the comment. In the comment section, you always get a feedback about which kind of calculation is relevant for this load case. So something which is quite important is that you need to put the right sign into the loads or the forces. So a positive force here is a tension force to the section. If you want a compression check, you need to add it as a minus. This is very important. So just add the minus, and you see that this command has changed from the tension to a compression parallel to the grain. And they also give an indication about which kind of formulas are going to be used in the check. So we're going to the result details. In general here, everything is listed, which is always, but just the values in yellow are the ones being calculated at this specific load case. So in that case, you're getting a valid result for KH and KHB, which are some values which you need for the calculation. And for the tensions or compression parallel perpendicular to the grain, you're getting the utilization factor of the specific point in the Eurocode. So in that case, 0.614 in the Eurocode is the one which is going to be plotted. All the other ones are not relevant. Also, the compression perpendicular to the grain is not relevant because we have a 0 degree alpha, and there is no shear or notch at the support. We don't have any torsion problems, and we don't have any compression stresses at the angle to the grain. The stability of the member is actually calculated, so here you see the intermediate result of this calculation. Those can also be checked by hand, of course. So if you're going to make a hand calculation, you can go to these values to check if you have done a correct calculation. Yeah, and that's more or less. So if we just make a quick change back again, you see that it's going to be tension parallel to the grain now. And those stability member values have been grayed out again, so they are not relevant anymore. Our revisions are not updated, to be honest. And as always, you have the license. Everything here which is distributed on GitHub has been released under the GPL version 3. So if you need any more information, please go to this site. So that was just a quick introduction to the ultimate limit state of these timber constructions, and we'll have a quick look at the connections with metal fasteners in the next video.